Making bread is an art. Sure, there are recipes, but any seasoned baker will tell you that they add a dusting more of flour here, splashing more water there, depending on any number of things, from the season to the amount of humidity in the kitchen that day, and so on. So if the dough is constantly changing, how do we know how long to bake it? Since our sourdough starter demands we make a loaf every week, we don't want to play a guessing game all the time. We might start writing down our observations. We notice for every 100 grams more flour, it takes 5 fewer minutes. But for every tablespoon more water, we add 2 minutes. Change the salt or yeast, more time changes. And before long, our bread artistry has left us with this: math. And without even realizing it, we've created our very own rational expression, or when two algebraic expressions are written as a ratio or comparison. If we just come across this in a book, it would be terrifying. In fact, one of the most difficult areas of algebra for people can be dealing with rational expressions. They combine variables and fractions, which makes them look just doubly intimidating. But there are really only 4 key rules behind manipulating fractions. And if we know how to apply them, we can turn out a perfect loaf every time. G'day, I'm James Tanton, and this is Study Hall Algebra presented by Arizona State University and Crash Course. One of the standard introductions to fractions is to imagine them as parts of a whole, like slices of a pizza. Okay, it's a little cliche, but I do like pizza. But when it comes to multiplying 3/4 by 5/7, that's harder to visualize. So then we start to think of fractions as points on a number line between integers, or maybe as percentages. And none of these models seem to add up. Now, I'm going to admit right now, right here, that there's no one perfect way to understand fractions. But all those partial truths we've learned can help us come up with 4 basic fraction rules that pretty much cover any time your professor might have waved their hands and said, and the algebra is trivial. Basically, here's the way I like to think about it. A fraction is simply a number that is the answer to a sharing problem. For example, suppose I have 6 pizzas to share equally among 3 people, and that makes for 2 pizzas per person. The fraction 6/3 is the number 2. So here's fraction fundamental number 1. If I have 6 pizzas for 6 people, each person gets 1 pizza. Whether it's 15 pizzas for 15 people, or 423 pizzas for 423 people, still 1 pizza per person. Basically, A pizzas for A people amounts to 1 pizza per person, no matter what A actually is. So when you see x plus 5 over x plus 5, we know that's just a fancy version of 1. Here's fundamental number 2. Let's say I'm less generous about sharing, and I have 6 pizzas for 1 person, namely moi. That makes 6 pizzas per person. Lucky me. So 3x minus 2 pizzas over 1, still all for me, no matter what x is. In general, a over 1 will always be a. For the third fraction fundamental, let's go back to 6 pizzas and 3 people. Suppose now I want to be generous and double the amount of pizza each person receives. Let's write this as a ratio. If everyone wants twice as many pizzas, we need to start with twice as many pizzas. That will give us 12/3. To triple the amount of pizza each person receives, we'd have to triple the number of pizzas we started with, and so on. In general, to increase the amount of pizza each person receives by some mystery number n, we'd have to multiply the number of pizzas we started with, or the numerator of our fraction, by n. But what if we doubled the number of pizzas and also doubled the number of people? Everyone still gets the same amount of pizza. We have more pizza, but it ends up getting shared to more people. Same if we tripled or 100-tripled the pizza and the people. And this gives our fourth and final fraction fundamental. If we multiply the top and bottom of a fraction by the same constant, the fraction does not change. K times A over K times B is just the same as A over B. It sounds obvious, but this fourth property is actually behind all the arithmetic involving fractions. For example, it's the principle we use to reduce or simplify fractions by writing them with smaller numbers. And many people like to think of this as factoring out a K on top and a K on bottom to get K over K, which we know is really 1. So maybe we're asked to simplify x squared minus 4 over x minus 2. Now, if there's any chance of reducing this fraction, we're going to have to find an x minus 2 in the numerator, because there's really nothing left to factor on the bottom or the denominator. To solve this, we might remember the difference of squares, a sneaky pattern that says anything that looks like x squared minus a squared actually factors into x plus a times x minus a. We know 4 is 2 squared, so x squared minus 4 would become x plus 2 times x minus 2. Or if you're like me and were never good at memorizing rules, you might try to work backwards and use educated guesses to figure out if there's anything we can multiply x minus 2 by to get x squared minus 4. In fact, there is x plus 2. If we multiply out x minus 2 times x plus 2 using the distributive property and our rectangle friends from last time, we get x squared plus 2x minus 4, which simplifies to x squared minus 4. And if you're still wondering where this x plus 2 came from, don't fret. We'll see more of this backwards thinking in our episode on polynomials. But no matter how we get there, we can rewrite our expression as x plus 2 times x minus 2 all over x minus 2. Aha! Now we see that there's something on the top that looks exactly like something on the bottom. The x minus 2's factor out, become 1, and basically disappear. And the entire thing simplifies to x plus 2. Does this ugliness really exist in the world outside of math class? Well, let's take a closer look through the math goggles. Hang on, what are these? I guess I left my math goggles in my lab coat. Okay, these will also work because different scientific disciplines are all connected by the language of math. And now we're chemists in a lab. So we know the heat capacity for any material is equal to the amount of heat applied divided by the material's mass and its final temperature minus its initial temperature. We have this piece of aluminium, applied some heat to it, and now we want to know what its final temperature will be. Because this pattern works for any material, and mathematicians, chemists, are lazy, aka efficient, we'll try to move the variables around to get something we can reuse and plug in our numbers last. So we need to get the final temperature by itself on one side. The expression final temperature minus initial temperature is in parentheses, so we can't move just part of it. But if we multiply both sides by this phrase, then we'll have a k over k situation on the right side, and we know that will reduce to 1. Now we have this equivalent equation. Let's divide both sides by heat capacity. And now we can take off the parentheses because there's nothing else multiplying or dividing that expression. Almost there. Add the initial temperature to both sides, and we've got it. An expression that will give us the final temperature no matter how much heat we apply, what material we choose, or what the initial temperature is. So now, let's say that we had a 0.75 kilogram piece of aluminium, originally at 20 degrees Celsius, and we applied 150 kilojoules of heat to it. We know from past experiments the heat capacity of aluminium is 0.9 units. So that makes about 222 degrees Celsius plus the original 20 degrees. 242 degrees Celsius is about 468 degrees Fahrenheit. So if this were an aluminium sheet pan, it's gone from room temperature to hot enough to bake a pizza. If we know our fractions, we can manipulate variables with ease and write general equations which we can reuse as they describe multiple situations in the world around us. Now you might be asking, do these rules really cover everything? Let's look at something we can't factor. What if we're asked to simplify 1 plus 1 over x over 1 over x? When I look at that, my brain just shuts down for a second. Honest human reaction. But then I take another look and ask myself, what don't I like about it? It's the fractions within fractions. So I need to get rid of them by making them turn into 1 and go away. If we could turn the 1 over x's into x over x's, that would be it. So let's try multiplying the top and bottom each by x. This gives us x plus x over x all over x, thanks to fraction fundamental number 4. And applying fraction fundamentals 1 and 2, this awkward algebraic expression is revealed to be just x plus 1 in disguise. So, rational expressions usually look worse than they are. But if you're faced with one and don't know where to start, here's some things you can do. If you're asked to simplify a rational expression, look for powers of x, like x squared and x cubed, and see if you can factor them into something that will cancel. Or look for constants you can cancel by factoring them out, both from the top and the bottom. If there isn't an obvious way to factor, or if you just want to get rid of some fractions within fractions, multiply the top and the bottom by whatever is in the denominator. And I mean it when I say, be careful to multiply both the top and the bottom. Otherwise, you'll change the original ratio, like changing 1/2 to 1/20 accidentally. And when you're working with formulas like in physics or chemistry, it's often easier to solve them if you keep them in variable form while you're rearranging the equation, and then put the numbers at the very end. Next time, we'll explore a very curious question in mathematics. Have we found all the numbers? What else is out there? Until then, cheers. Thanks for watching Study Hall Algebra, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video and want to keep learning with us here at Study Hall, be sure to subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.